So we'll continue in section 2.4, and now we'll get into the derivatives. That's the topic of the section, but we definitely needed to have some limit problems. Again, few in the homework. I kind of wish there were a couple of extra, because that is an important section, and you should definitely anticipate a couple on the test that goes with this chapter. But overall, the biggest topic that we want to get used to in this unit is the derivatives. So 2.3, we learned a lot about shortcuts with derivatives. And now the rest of this video, what are the derivatives of the trig functions? Some practice using them. So I've got sine worked out. If my original function is sine x, this is our limit definition. Sine x plus h, f of x plus h minus f of x all over h, limit as h approaches 0. But now, again, remember, you're going to get the result. That's what you're going to need. But I want to show you where that comes from. And I'm going to use the angle addition formula. Now, last video, when we were dealing with the sine u over u, I was very firm about we don't break up these angles. I will do this, and this is pretty much the only time we're going to see this semester. It might come up a touch in Calc 2, but really, again, the angles inside are untouchable, but this is a perfect sine A plus B. So if I use the angle addition formula, I get sine A cosine B plus sine B cosine A. That's the angle expansion. If you think of it in terms of u and v, sine of u plus v, sine u cosine v plus sine v cosine u. The minus sine x is still there, and it's all over h. Now, what I'm going to do next, I'm going to bring this to here. Just changing the order. Instead of plus a minus b, I'm writing minus b plus a. Still being thorough, still keeping my limit notation. So sine x cosine h minus sine x, and then I've got the plus sine h cosine x. All of this is over h, but I'm now going to break it into two separate fractions. Again, realize that's a legitimate move. We're, again, much more accustomed to taking two separate fractions, addition, subtraction, getting a common denominator and bringing them together. But this was where, again, I need that opposite move. Where do I go from here? Well, the reason this works is because now I've got a sine x that can be factored out of the top. Cosine h minus 1 would be left behind, and that's still over h. Plus, and now again, just changing the order a little bit, I'm going to throw the cosine out in front, and I still have sine h over h. Do you see the two identities? Cosine h minus 1 over h, as h goes to 0, we had it as x's, but this goes to 0. That's a known trig identity, trig limit identity. Come over here, it's perfect. Sine of h over h as h goes to 0. Recognize, everybody, h is the variable according to this limit. So the sine x, don't plug in h is 0 here. Same thing, cosine x, don't plug in h is 0 here. But there's an identity, and this goes to 1. 0 times sine plus 1 times cosine equals cosine. So we've got our first result. The derivative of sine equals cosine. Now, I can do long proofs like this for all the trig functions, but now I want to start just getting to the results. Again, it's nice. It's very good. It's a very good part of expanding your mathematical understanding, giving you a little more experience. No matter which math class you go to, it's really good to enhance, to have more experience, to see different possibilities. But again, our big priority is knowing how to use these. But just in this proof to realize, that's why I had to give you those two identities, because we needed both of them. Both those identities relied on the h in this case being in terms of radians, and therefore the derivative relies on the angle being in terms of radians. So that's why, again, it comes full circle. That's why there are no degrees in calculus. We only consider angles in terms of radians. It's for these results. Technically, there's a second reason. Degrees are actually like a man-made unit that gets in the way in a lot of problems. Radians, even though we treat them like a unit, they're all based as an angle on the proportion of how far around the circle have you gone. So technically it's proportions and they're unitless. But no matter what, the end result, we need radians. Okay, so there's my first derivative. The derivative of cosine is negative sine. Now I'm going to keep going, everybody. I'm going to rattle off. We got 4 more trig functions. We need 4 more derivatives. And even though we've spent a lot of time doing other things, that is by far the biggest thing. Sine and cosine are without a doubt our primary 2 trig functions. They get used a ton throughout Calc 1. But then the others, they still come up often enough. So that's why we mention you should know some trig facts, but the biggest thing for Calc 1 is getting the trig derivatives. Good practice, good understanding, and then the other things, knowing some trig values like we needed for this limit problem. We'll need things like that when we have tangent line problems, questions about tangent lines. Those ideas will come back. We'll have some other situations later on where we need some right triangle SOHCAHTOA facts. So again, just to realize the derivatives are such a key. So keep my list going. The next function I'll list is tangent, and that has a derivative secant squared. The derivative of cotangent has a derivative negative cosecant squared. And then our last 2, just for room, I need a little more room, so I'll write the derivative here. The derivative of secant is secant tangent. And last, the derivative of cosecant is negative cosecant cotangent. Notice these last 2. You're getting 2 trig functions here. They both get the angle x. Don't make that little mistake. Don't write secant tan x for this. Make sure you get in the good habit. Even though a lot of us just read it, the derivative of secant is secant tangent. Make sure you get the x in both of these. So this is our list of the basic trig derivatives. Again, you're going into Calc 2, you better memorize this list. Good possibility we may be back in person next semester, so you would definitely be expected to have this list memorized. For this semester, of course, you could always go back and refer, but thinking about memorization, writing it out. Write the list out. You go to do some homework, don't just flip back to these notes, write the list again. Remind yourself. Okay, remind yourself the derivatives. Maybe instead of using this notation, you'd rather make it more like an F prime column. So you could just write sine x, cosine negative sine. Whatever way you prefer to write it, the more you write it out, the better it will stick in your brain and help you memorize those results. Couple of little things. Very often, the negative signs. That's an easy little place to make little mistakes. So realize, how do you know when the trig function derivative should be positive or negative? Well, notice, any trig function that starts with a cosine, cotangent, cosecant, the co-trig functions are all the ones that get the negative derivatives. And then the other ones are positive. Sine, tangent, secant. None of them have that co-prefix at the beginning, and none of them have negative derivatives. So that's a way to help keep some of this straight. The second thing, sine and cosine, again, they just come up way, way too often to not have those memorized. But then for the other ones, there are little tricks. The co gets a negative, but look at the relationship. Tangent has a derivative secant squared. Cotangent gets the negative, and then as derivative, cosecant squared. Maybe you just thought I was just emphasizing the co, but the derivative here directly leads us to the derivative here. These functions are related. Add the co in front of this word and you get this function. And then they're derivatives. Add the co in front of this derivative and you get this derivative. So you start with the co, you get the negative, and by knowing tangent goes to secant squared, therefore cotangent goes to cosecant squared. And we get the exact same result down here as well. Regular secant gets secant tangent. Well, now it's cosecant. The co gets me the negative. And then instead of secant tangent, I get cosecant and cotangent. So once again, some people still feel like they just hear me emphasizing the word co a lot. But for others, that really helps them memorize this a little bit. Whatever works for you, 6 functions, you need to know these derivatives. Now, I still want us to practice, but just before we jump in, I formally proved this, gave you this result. I'd like to then also do quick proofs for these. But these quick proofs, I'm not going to use the limit definition. I'm going to take advantage of already knowing these derivatives. So, if I said, find the derivative, and my first function is tan x. Now again, we've got the result. The result is going to be secant squared, but where does that come from? You want to have this memorized, but look what you could do if you're in a pinch. You could treat tangent like sine over cosine, because that's what it is. And now by making this move, I'm forcing myself to use quotient rule. But that's okay. Quotient rule, derivative of the top, the derivative of sine is cosine. That's a known result that we proved. Times plain old bottom, minus the derivative of the bottom. Well, the derivative of cosine is negative sine. I gave you. I didn't prove that result. I could, the same way I proved this. Use cosine of x plus h. Use that expansion formula. There's even other ways to do this as well. But point right now is to get this next result. So the derivative of the bottom is negative sine times plain old top all over bottom squared. Now you may be saying, well, how is that secant squared? But look how this cleans up. And this is partially why some people don't like the trig functions. It's like you learn derivative rules, but there's so many ways to overlap. This is not the derivative of tangent. That's just the original definition of tangent. That's a manipulation, not a derivative. But now we've got a whole separate derivative. So there can be a lot to keep track of. But again, make sure you're clear. Don't just say tangent equals secant squared. The derivative of tangent equals secant squared. Tangent as an original function equals sine over cosine. But now down here, let's clean up a little bit. Cosine times cosine, that's cosine squared. That becomes a plus. Sine times sine is sine squared. That's a known identity. That's 1 over cosine squared, and 1 over cosine is secant. And that's how the final result is secant squared. So you could always prove this result in a pinch by just, again, prioritizing and knowing the derivatives of sine and cosine, but this is still going to come up too often to do this every time, right? So we definitely want to know this result. Especially, let's jump right into number 2. This was a little bit more of a demonstration, but now number 2, let's find the derivative. And let's already jump and take advantage of some use. If I had x cubed times tan x, that's product rule. And that's one, unlike when we first learned product rule, it felt like we could really avoid it. We could always see the multiplication situation, but then multiply, FOIL, distribute, and then get rid of that multiplication situation. Sometimes it was easier than other times. But in this situation, you're stuck. You can't multiply the x cubed to make that tangent of x to the 4th. This is stuck. But you have multiplication, so you're stuck using product rule. Derivative of the first times plain old second plus derivative of the second times plain old first. Now, our book, this is a little bit of a better habit. When you mix regular variables with trig functions, it's a good habit to move them to the front. This is correct, but it's so tempting for people to start multiplying the x times x cubed here. So again, for that reason, a lot of people like to move those to the front, so that kind of provides a little distance so they don't accidentally do something that they can't. So this plus this is the best derivative we're going to see for this function. But if you didn't already know the derivative of tangent of secant squared, and you had to do all this work just to get that result, again, you're taking a problem that should have taken you about a minute, and you're taking 5 minutes. Again, it's online. You do have some of that luxury, freedom of time, but still trying to get into overall good habits. So we got to use tangent and see a little bit of product rule. I want to show you quickly the same thing if you want to prove the derivative of secant. So let's look at number 3. C of x is secant x, but pretending I don't already know that the derivative is secant tangent, well, I can rewrite its original function as 1 over cosine. So now I can take the derivative in this form. This would again be quotient rule. Derivative of the top, 0, times the plain old bottom, minus the derivative of the bottom, times plain old top. Notice, everybody, that's the second time I'm using quotient rule, and I also did a product rule. If you still want to write out u is 1, v is cosine, get your u prime as 0, v prime as negative sine, then plug it in. Similarly with product rule, u is x cubed, v is tan x, u prime is 3x squared, v prime is secant squared, then plug it in. There is no shame or problem at all with doing that. No problem at all. So if you need to do it that way, make sure you do. That's just one extra line. It's no issue at all. But again, I'm just trying to show you, if you know the rules well enough, you could just kind of go right along, taking derivatives and originals and plugging them in as necessary. So u prime v minus v prime u all over v squared. 0 times cosine is 0. This becomes plus sine times 1, so that's sine. And now it looks like we got sine over cosine squared. But if you break up that cosine squared, and again, think of this as two separate fractions, so what I need here is a 1 over. You have sine over cosine, which is tangent, times 1 over cosine, which is secant. It's just, again, common. Here we got tangent times secant. Here I wrote the rule of secant times tangent. Same thing. Exact same thing. So number 3 is, again, a little bit more of a proof. And we shouldn't have to do that. There's like 2 in the homework problems where they try and get you to duplicate what I showed you to prove this derivative is true and to prove this derivative is true. But for the rest of them, we want to just know those derivatives and use them. So for number 4, let's look at d of x, and let's look at 5 sine x minus 3 cosine x plus 2 cosecant x. Still taking the derivative, still want to have good approach. What's the situation here? Well, back in number 2, quickly, x cubed times tan x. That was multiplication. We couldn't clean it up. That's why we needed product rule. But now number 4, now it's 3 separate pieces, and those pieces are separated by addition, subtraction. This is our ideal. Take the derivative one piece at a time. So I'm just going to jump right in. D prime what happens to the 5? It pushes along, right? Just like if I had a quick reminder, 5 times x cubed, hopefully you're already getting into the habit, the derivative of that, we would just say is 15x squared, but formally it's the 5 pushes along, and then the derivative of the x cubed is 3x squared. Again, good habits, we just already multiply that. But that's still the same rule. Don't let the 5 bother you. Don't use product rule here. Push the 5 along, and the derivative of sine is cosine. Minus 3 pushes along. The derivative of cosine is negative sine. But do you notice I've got a little mistake? I paused here for a moment for a reason. And do you realize the issue here, this rule says it's still c times the derivative of the function. And if you leave this the way it is, you've got minus 3 minus sine. This needs to be minus 3 times minus sine. So for some people, that little bit, the co-trig functions, getting a negative derivative really flips the sign that you started with. So no issue here. The derivative of sine was positive cosine, so nothing extra to worry about. If this was a minus 5 in the first place, it's a minus 5 times cosine. But here, this actually would become a plus 3 sine x. No harm leaving it like this, but then again, certainly cleaning up or just realizing when the book cleans it up, these are the same thing. And same thing here. The derivative of cosecant is negative cosecant cotangent. So some of us just get right in the habit. Don't put plus 2 and then the minus. Kick the negative out in front. Minus 2 cosecant cotangent. And again, don't lose one of those x's. Don't write CSC, COTX. Each of them are individual trig functions. They each get their own x. Okay, number 5. This is going to be my last basic derivative, everybody. I've got a few other things I want to mention, but other than this, it's basically just you've got your list, practice the rules. And even though they're kind of already in different forms, we've already practiced both product and quotient rule with the trig functions. Let's get another one like that. Number 2 is a forced product rule problem. Let's look at number 5, e of x. And for e of x, let's look at x to the 5th plus, let's do minus. X to the 5th minus 2 cotan x all over, let's say, secant of x plus 4. I did show you quotient rule by just plugging in and doing those little pieces one step at a time. But now this is a little bigger. It's a little uglier. Definitely have division that we can't clean up. And by the way, everybody, I mean, if you started off with something like your function was sine over cosine, that may start with division, but we can clean that up. And again, now that we've got the result, if you started with sine over cosine, this would definitely be the long way. The short way would be rewrite that as tangent. Now there's no quotient rule, and that's just a known trig derivative, and you're done. But here, there's no simplifying that, right? There's no way we can clean that up with any little quick shortcut or anything. So it's a little bigger and messier. I'm going to write this one out. X to the 5th minus 2 cotan x v secant x plus 4. So now that's just simple subtraction. U prime 5x to the 4th plus 2 cosecant squared, just like we saw here. I'm getting an extra negative. The derivative of cotangent is negative cosecant squared. I just already kicked that to the front to make that a plus. And then v prime secant x tan x plus 0. So my derivative, a reminder of the rule, u prime v minus v prime u all over v squared. So specifically applying that to this problem, u prime 5x to the 4th plus 2 cosecant squared, all of that times plain old v secant x plus 4 minus v prime secant x tan x times plain original u all over v squared. Tempting, but that does not simplify. And this is another very good example. We had no choice. We had to use quotient rule. We had a very big, messy answer. And there's really not too much we can do here. I mean, even if you FOIL this out, distribute this, your answer is just still huge and ugly. I'm just going to leave it exactly the way it is. Okay, number 6. You know what, actually, we'll save that for the next one. All I was just going to do was one quick one where we could see how product and quotient rule can mix together. You know what, let's do it. Let's do it quickly. Number 6, let's look at f of x. Let's look at x squared sine x. And let's divide that by cosine x plus 5x. Now, we can't just make that a tangent. There is no dividing, just individually dividing those two. So now this is a good situation. Big picture is division, so I would use quotient rule. But when you write out your u and your v, notice u is not straightforward. U still has multiplication, so you would still need product rule. So to get u prime, that would be product rule, but this isn't too bad. Maybe, again, a little more bookkeeping. If you're going to do more bookkeeping, don't use u and v again. You need different letters. U and v are already being used. Use like a and b. And now translate your rule into a prime b plus b prime a. But I'm going to get the result. Derivative of the first plus the second times the second plus derivative of the second times the original first. And I'm already going to make that a little nice and neat. V prime negative sine x plus 5. So now, for room, I'm going to have to squeeze this in a little bit. But now it's all set up. Yes, that was product and quotient rule, but we started with a big division, so we were thinking about quotient rule. But then when we started to apply our quotient rule, we realized we still needed more. It's still an early introduction. Again, this is why 2.3 is such a key section. Get all those little rules worked out, get your practice. We'll have a quiz just on that section, and you're going to need that because everything builds on that so that we can see higher derivatives. I don't want to necessarily call them higher because people think about taking multiple derivatives, but I'm thinking more about the idea of just tougher derivatives, derivatives that mix more rules together. So this u prime v minus v prime u all over v squared. I'm not even going to squeeze that in. It's going to be too messy and I'd run out of room. So, but you could fit that in using that. Couple little things just before we end this. As I suggested, we still have one more rule to go because all the trig functions we've seen are basic trig functions. They're always trig function of x. But what if it's sine of x squared plus 1? That's not multiplication. And whether that's a nice algebraic function or not, sine of cosine of tan of 6x, that's not multiplication, and neither is this. This is inner outer. This will be a function that has layers, and in 2.5, we'll talk about the chain rule. And that's something that would directly apply the chain rule. And that's a harder example, but just to point out right now, neither of these, there is no multiplication in either of these situations. These are all about inner and outer. And that's going to be something, a last rule. It's not just here. It's not just trig functions. We know how to take the derivative of x squared plus 1, and we know how to take the derivative of the square root of x, but what if it is the square root of x squared plus 1? That has inner outer layers. So again, there's still one big rule left And then after we finish that rule, then we'll start just mixing everything together and seeing, I don't want to scare you, they're not really that tough. They're tough initially, but with good practice, this is all a lot of bookkeeping. And it all relies on looking at the situation first. Don't dive in and start taking derivatives. What is the situation? What rules? And then, are you ready to go? What are you setting up? Then you move. That's the thought process to go with it. Okay, after we do that, we'll also get more of practice with the equation of the tangent line and horizontal tangent lines. But here is our last problem for today. Let's find where the function f of x equals to 2 cosine x minus x plus 5. Where does this function have horizontal tangent lines? We've asked that already. That's a big question that's gonna come up more and more and requires the use of a derivative. So that's where we're going. We're gonna find the derivative and set it equal to 0. But one last little catch. When we have trig functions, I'll always include this little on the interval 0 to 2 pi. I'll always include that with this type of problem in a trig function, just because, remember, the trig functions just keep repeating over and over again. So any of these situations, you'd have infinite answers. Let's just keep our answers one loop around the unit circle. But notice again, I didn't say 0 to 360. We're not in degrees. We need to think in terms of radians. So it's trig, but it's still the same idea. Take the derivative, nothing too fancy here. 3 pieces separated by addition, subtraction. So derivative of the first minus the derivative of the second plus 0 for the derivative of the third. And horizontal tangent lines have a slope of 0. The derivative gives me the slope of the tangent line. When does this equal 0? Solve this for x. Okay, good reminders with trig functions. Before we can solve for x, we solve for the trig function. Add 1, divide by -2, plus 1 divided by -2, we'd get -1/2. When does sine equal -1/2? Use the calculator, you get one answer, and you don't even get an answer on this interval, okay? And especially if you're in degree mode, you still got to convert. This is where, again, know some trig facts. How do I answer this? Well, I remember sine is negative in the third and fourth quadrants. So I'm going to get 2 answers. What angle, what reference angle connects sine to 1/2? That's 30 degrees. Again, pi over 6, but I'll show you how you could think in degrees. So that's basically the setup, but we need our answer measured from here. So if this little piece is 30, it's 180 to here, this would be 210 degrees to here. Do that again and get to here. Well, if I keep going, it would be 360 degrees. I would have completed the circle, but I came 30 degrees short of that, so I got 330. And now you can do some converting to radians, and this one will equal 7 pi over 6, and this one would be 11 pi over 6. Those are the answers, and we are done. But very quickly, I showed you, again, there's no harm, just because we're in radians, there's no harm in thinking in degrees and then converting, either converting at the beginning or converting at the end. Here it would be at the end. It seems like the easier answers, but you convert at the end. But you can just get the practice and think in terms of radians. Instead of 30, think of it as pi over 6. This is pi. You went past pi by pi over 6. 1 pi plus 1/6 pi is 1 and 1/6 pi, 7/6 pi. Over here, all the way around, instead of 360 is 2 pi, but I came pi over 6 short. So 2 pi minus pi over 6, make that 2 pi over 1, get a common denominator, and there's your 11 pi over 6. So the same thinking you're doing with degrees, 30 degrees short of 360 is 330, you can just do that thinking with radians right off the bat. Some of us don't have as much practice with radians, so again, degrees is a little more natural and I completely understand, but it's not bad to get practice with the radians.